Hello. Uh, am I audible? Someone please confirm whether I'm audible or not. My voice is clear to you or not.
Yes, you are
Yes,
audible.
yes, yes.
Thank you. Just a minute. I will start in. Okay. Okay. So, good evening, everyone. Um, Welcome to all of you to the live tutorial session of the NPTEL course Linear Algebra. And let me introduce myself. I am Milan. I'm Milan Kumar Mal from IIT Madras. So I am going to conduct live tutorial session on each Friday from 7 p.m. to 9 p.m. and till the end of this course. And if there is any change in the schedule, I mean there will be, if there is any change, that will be very less and hardly once or twice, but not more than that. Usually it will happen from in each Friday from 7 p.m. to 9 p.m. So the main target of this tutorial session is uh, that I will address any type of doubts you have throughout this course, uh, or which and I'll try to solve some problems which may help you to solve the weekly assignments and understand the materials which is uploaded by the NPTEL team and the course faculty. And I hope those discussions may help for all of you, and also that may help me to understand things more better and more great way. And we'll learn together and to for better understanding and better interesting way to learn the subject and learn this beautiful mathematical topic. So so what I'll do usually, I will request everyone, if you have any problem, any problem in the sense, if you have any doubt regarding in this course material, or regarding any problem which is not able to solve, which are not clear to you, you can send those problem to me in the email ID that I'm writing, that ma21d018 at the rate smail.iitm.ac.in. And I'm also writing that in the I'm also writing that mail ID in the, yeah. So I'm writing that mail ID in the message. So if you can 21d01. If you have any doubt, any questions are not clear to you or not able to understand clearly, you can send a mail to this mail ID, and I will try to address those problems in the next tutorial session. Otherwise, you can also ask me in this live tutorial session whatever you have any doubt, or whatever I am trying to explain, or whatever the uh, course videos. If there is any doubt to you, you can ask me here. I'll try to solve those problems according to my understanding. And so so let's start. So what I'll do, I will usually do some problems which I have prepared. If you have any problem, you can tell me. I'll try to solve those problems in fast, and then I'll try to address the problems which I'm planning to discuss. So okay, so this is the tutorial one.
Can you hear me, sir?
Yes, yes.
In the problem set of one, actually, I have joined Tuesday, so I am completely new here.
Mhm.
I have not submit the problem set one till now. I have taken the problem from the problem 1.1a. So the asks that to check class is group or not.
Yes.
For that. there is a statement that at least one positive integer and at least one negative integer. What does mean that all the negative integer or all the positive integer not belongs to them? At least,
Sorry,
what does mean at least?
which problem you're talking about? The first assignment, first problem.
Yes, week 1.1.
Yes. So there, which problem?
1.1a.
Okay, just a minute. Let me check. 1.1. Achha, 1.1. Yeah, okay. You want to. Okay, that's the problem you need to submit. Okay. So what this problem says, let G be a subset of integers which contain at least one positive integer and a subset of integers and at least one negative integer. Suppose that G is closed under the usual addition in Z, that is A plus B belongs to G whenever A belongs to G, that G plus is a group. So what's the question?
Yes, actually, for Z, since the inverse property does not use this should not be good, okay. But in this question, the line which contains at least one positive integer and at least one negative integer, this line, what does it mean? That all the positive integer, all the negative integers, that's what belongs to Z.
No, that's not necessary. Here it is saying that G just considered as a set, okay, that contains at least one positive integer. I mean, if you say that there exist A and B, two positive integers, such that minus A belongs to G and B also belongs to G. That's the guaranteed thing. Okay. Now, and also it is considering that if you have two elements A and B in the G, then their addition will also be there. That's also the standing assumption. So under that assumption, you have to prove that whether G is in group or not. That's what it is. So basically, something like that. For example, let me tell you one thing. Suppose you have minus one, or suppose you have minus two, and it is claiming that if A is there, B is there, then A plus B will be there. So minus two is there and minus two is there, then minus two plus minus two, that's minus four is there. So that's what it is. Okay. So that means if an element is there, then all the integer multiple will be there. And I hope that's the good enough hint. Uh, and there is another hint: use the minimum principle. So that means you have how to use the minimum principle. I am not supposed to explain much more because this is the problem, assignment problem, but I'm trying to give as much as possible without explaining the complete solution. That if you have suppose you have there is at least one negative integer, so you will get an highest number of time things, right? There is one at least positive integer, you will get the lowest positive integer there. Okay, something like that, and you have to, after that, the hints I have said earlier, you have to use that, and I hope that will help you. So that what is mean that there is at least one means when you use the minimum, their minimum will exist. That's what it is, the main point. Suppose you have minus 2, minus 4, minus 6, something like that. There exists a minimum in the sense that there is minus 2, and you can use the what I have said, that A plus B is there. So minus 2 plus minus 2 minus 4 has to be there. That's the necessary. This type of things. I hope this may help you. Okay, so what I have tried to said is that clear that you have guaranteed there exists one element and you have the minimum one. You have to consider that minimum one, and from there you have to generate type of things. You have to do some. Okay, even if you are not clear to you, I will completely solve this problem in the whatever the next week will come, where the assignment submission date will be over. After that, I am permitted to explain that problem, especially the blue line problem, which is supposed to submit. Okay. Any other doubt? Anyone? So okay, let's begin whatever I have prepared. Uh, even in between, if you have any doubt, whatever I'm trying to explaining, you can stop me and ask me, and I'll try to solve that one. Or even in between, if you have any other doubt from the course material, you can even ask me those things again. Okay. So one problem actually I have prepared some few problems which is from that assignment, which is not blue colored. So I will try to explain those problems. So this is the one of the problem in the what is called the week one content, that exercise sheet. So what this problem says, that Let's start with the binary operation on the set of all positive integers z plus. That's not only z plus. This is all positive integers greater than equals to 1, and we are giving the binary operation by n star m. That's the GCD of mn. Okay, that is the greatest common divisor. That means greatest common divisor is the means. What is mean by GCD? I hope everyone know that if m and n two positive integer, if m and n two positive integer, then GCD of mn is the greatest common divisor. Means GCD mn is the positive number, is the positive integer, such that GCD of mn that uh, should divide m, and GCD of mn that should divide n, and any other divisor c, positive divisor, any other positive divisor c satisfies the condition that c divides GCD of mn. So GCD of mn is such number uh, such that if you GCD of some is the such divisor that will be divisor for both m and n, and that is the greatest one. That means if there is any other divisor that will divide the greatest one. Okay, this is the GCD, and similarly LCM. So this is some definition, basic definition. So what I will do in this, mostly I will try to explain some problem, or try to solve some problems which are related to the basic materials. These materials are not core material of the linear algebra course, but they are very required and fundamental materials which is needed to start the course. And the LCM or least common multiple of mn, least common. Oh, should I be a little slow? That's what it is you are asking, right? In writing or am I speaking? Okay, in the speaking. Okay, okay, thank you. Okay, so I'll try to be a little slower. Okay, so what is the least common multiplier? Means that's the okay. Let me just a minute. Least common multiple of m and n. What that means? That means that that is some positive integer, such that m should divide LCM of mn, and n should divide LCM of m comma n, and any other multiple of mn, any other multiple, positive. In fact, we will mostly deal with positive, but negative is, you can consider that. But mostly, whenever we are considering LCM and the GCD, that they are considered as positive multiple. C of m and n satisfies the condition uh, that LCM mn divides C. That LCM is the least one. That's what it is. Okay. So with this, let's try to understand this problem. So here, if binary operation is given, that n star m is actually the GCD of mn. Here we have to first prove that this star is associative. I hope you have watched the lecture video which is uploaded in the NPTEL portal. So what is mean by associative? We have, whenever you have a binary operation, uh, associativity means if A, B, C belongs to some set G, where you have the we have the binary operation star, then A star B whole star C that is equals to A star B star C. So what is mean by this? We will first do the operation A and B, binary operation in between A and B, and then whatever the resultant, with that we will do the binary operation with C. Here it is means first I will do the binary operation with B and C. Whatever is resultant, we will do the binary operation with A, but this way A star B star C. First of all, note that here A star B star C, that's not necessarily equals to B star star A. This is not necessarily. So binary there of course depends on the order. So on which I mean depends on the order that depending on the binary operation. So be careful. You can't change the side that A star B is equals to that. That's not. Yeah. Yes. 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 Yeah, then I'm giving this whatever is giving here, that's the associative. But if you say in what cases this is not associative, I have to think a little bit. But there exists any binary. That's not very difficult to finding a binary operation which is not associative. Okay, let me tell you one binary operation. Let's take A is a line. I mean, here I will prove this operation is associative. Okay, I'll prove this operation is associative. But I am giving an operation where it is not associative or relation. Uh, Matrix multiplication is not commutative, it is associative. Matrix, yeah, yeah, exactly. Thank you, thank you. Suppose ABC just real number you choose, and the binary operation is A minus B. Then you can think like AB star C. That means A minus B minus C. That's naturally says that A minus B minus C. And if you do this B star C, that means you have A star and it is B minus C, and then it is A minus B minus C. That will turn out to be A minus B plus C. So not associative. Thank you. Who said Emmanuel, right? Thank you. Yeah, these are the just real number. You can just what is it? You can take real. Yeah. So whatever is GCD and the matrix multiplication is associative. That's not commutative. Commutative is separate thing. Will come again. But associative matrix multiplication is associative. Okay. So how this is associative? That's so. Let's take ABC three number. Let's take ABC three number from the group. That's the positive real number. Let A B C three number from the positive real number. Here it is means greater than equals all of them are greater than equals to 1. All of them are greater than equals to 1. So so let's take D1 is equals to GCD of A star B, and its uh, GCD of GCD of GCD of A comma B comma C. This is what it is the first term, and what it is last term is that I mean right hand side term is that GCD of A comma GCD of B comma C. This is what it is D1 D2. So what I have to prove the associativity, we have to prove that D1 is equals to D2. That's all. Nothing more, nothing less. Okay. So so as GCD means that greatest common divisor. So that means D1. If we from here, if we start to the D1 will divide GCD of A comma B, and D1 will divide C. So, but GCD by definition, GCD of A comma B that will divide A, and GCD of A comma B that will divide B. So that means D1 divides this GCD, this term, and this term divides both A and B. That means D1 divides both all A, B, C, A, B, C. Similarly, D2 divides A, B, C. But that's not enough to say that this is uh, that's not enough to say that D1 is equals to D2. What I'll prove that D1 divides D2 and D2 divides D1. So then that will help. Okay. So now as D2 divides A comma B, that means D2 should divide the GCD of AB, because GCD is the greatest common divisor and D2 is one of the divisor. So that means D2 should divide A comma B. But also we know that D2 divides C. Now D2, there is, consider this is a single term, this is a single term. Then D2 should divide GCD of A comma B. These are going through the just through the definition of GCD, right? So that means this is what it is. This is D1. So that means D2 divides D1. Similarly, D1 divides B and C. That implies D1 should divide GCD of B comma C. And also we know that D1 divides A. That means D1 should divide GCD of A comma GCD of B comma C. So that what it is, this is D2. So whenever D2 divides D1, that means D2 is less than equals to D1, and here it is D1 is less than equals to D2, that says D1 is equals to D2. Okay. So whatever I have tried to explain, that I am tried to through the definition. If you have doubt, please let me know. If you have not able to understand anything from here or not clear, you can let me know. I'll try to explain. I'm taking a little pause. So if you have any doubt, please go ahead. Okay, sure. Oh, okay. Yeah. Okay, let me once again explain. So what I'm trying to say, that I have assumed D1 is equals to GCD of this one. So by the definition of GCD, consider this as a single term. This is a single term. By the definition, D1 will divide this term and D1 will divide this term. Okay. So here what it is. And once again, this is GCD of AB. So this will divide A and this will divide B. Okay. So that means now what I have, D1 divides this term and this term divides A and this term divides B. That means D1 will divide A, D1 will divide B. Something like that. If you have M divides N divides P, all are positive integer, then M will divide P. This is what it is I am using here. So D1 divides A, B, C, all of them. Similarly, if we do the same operation here, that D2 divides A, D2 divides GCD of BC, and GCD of BC divides B and C. Then D2 will divide both B and C separately. That means D2 will divide A, B, C. So D2, so what I have obtained, that D1 is dividing all of ABC and D2 is dividing all of ABC. Okay. So now we have, till now it is clear that why D1 is dividing all of them and why D2 is dividing all of them. Okay. So now now let's again construct. How to construct? We have know that D2 divides ABC. So in particularly D2 divides A, D2 divides B. So that means by the GCD means greatest common divisor, and D2 is one of the divisor. That means D2 will be smaller than the GCD, and that will divide ABD, because the definition, if we go back, here it is GCD means that GCD is some number which divides both the number and any other divisor C, that C should divide GCD. Okay, so that means okay, so that means D2 divides GCD of AB. Is that clear? Because that's going to definition. GCD means that should divide both the integer, and that is the greatest. And greatest in the sense any divisor that will divide the GCD. Is that clear? Okay. So now D2 divides this one and this one. Consider this as a number, single number. So now as D2 dividing both the number, so D2 will divide their GCD. So that's what it is I have written here. And that is nothing but D1. Okay, so that means d2 divides d1. So that means d2 is less than or equal to d1. Now, if we go like the similar way from the other side, we will have the other around. How will go? D1 dividing B and C, that we know, that we already know. So D1 will divide GCD of BC. And also we know D1 is dividing A. So this, consider this as a single number. D1 dividing these two numbers separately. So D1 will divide their GCD. This is, and this is D2. So that's why D1 equals to D2. Because D1 dividing D2 means D1 will be less than or equal to D2. So D1 is D2. Is that clear? Is that helps? Okay. So what we obtained though, so the binary operation, so the binary operation star is associative. Okay. Okay. So this is the one of the main question here, that prove that star is associative. And the one is the identity. Here is a mistake. This one is mistake, and so this question will not be valid again. So consider z plus z. What is the notation they have used? Z plus above. So I should not write z plus here. This is z plus above. So z plus with the binary operation, that's GCD. So this one is a structure. What is the structure? You can take two elements, you can give a binary operation in between them. That's what it is we have, and we know that's a operation that is a that is an associative. A set with a binary operation, a set which is closed, a set S which is closed with a binary operation star, and contains identity. What is identity? I'm saying, and I'll just discuss. Contains identity or unity is called monoid. Sorry, we need the associativity. So here we have this structure. Okay, we know that with this binary operation, this is associative. What is identity? Identity, identity is an element. Let's take E in Z plus, such that A star E is equals to E star A for all A belongs to the set Z plus. Then we can say E is the identity of that set with the corresponding binary operation. If we have some such element, if we don't have such element, we will say that there is no identity. So here is what is the possible identity. Here we have taken Z plus, and Z plus is nothing but all those elements, all those integer such that n is greater than equals to 1. So what is the possible choice of the um, what is the possible choice of the identity? If we consider 1, so that means if we take the GCD with that element, so, so let's take 2 with 1, GCD of 2 1. What is GCD of 2 1? Greatest common divisor, that's 1, and that is supposed to be 2 star 1. But what we want, that has to be A. Okay, but we are not getting A here. We need to get A, then we can say the identity element. But we are not getting here. So, and I and we can prove, you can observe that there is no identity. Any integer, you can take any integer n, and and consider another integer m which is not equals to n, Then what is the greatest common divisor? M star n has to be either that's not 1 or n. I mean, if you take n and any other integer which is still greater than n, okay, then either it will be n or something which is less than equals to n, right? It will be always less than equals to n. Greatest common divisor of two integer, that will be always less than equals to the minimum of of them. So that means what I am trying to say, if m and n are two positive integer, then GCD of mn, that has to be always less than equals to minimum of m and n. Okay, so that means you can choose any integer and take some bigger integer from positive integer and take any bigger integer from that, and if you try to find the GCD, greatest common divisor, that will always be less than equals to n, because that term has to divide n at least, and if that term dividing n and m, that has to be less than equals to n and m both. So that means that term has to be less than equals to minimum of m and n. Okay, so from there you can say choose anyone, and if choose m which is not equals to m and m is greater than 2n, so then GCD will be not n. GCD will be at least n and at max n or less than n. But we are supposed to get m again. If we choose n is the identity element or a unit element, then we are supposed to get n star m, supposed to get m, but we will not get that. So that's why there is no identity element. This binary operation on Z plus does not admit any identity element. Is it clear? If you have any doubt, you can feel free to ask. I'll try to explain, because that's what it is. That's what it is. I am trying to. That's what it is. I am supposed to do at least. So what we got, that there is no identity in this binary operation. Okay, and if we had the identity, then what will happen? Then we can ask the question of invertibility. What is the invertibility? If we consider an element A in the Z plus in any group, not group, any set G with the binary operation G star, then and suppose we have the identity E, we have the identity. We are assuming right now we have the identity. Then then inverse of A is an element B in G such that A star B is equals to E is equals to B star A. Then B is said to be, yeah. Hmm. No, no. Yes, that's true. But here star is GCD. Here star is GCD, right? Here star is GCD, not multiplication. Star means not multiplication. You can see that most of the time star is plus or addition or multiplication, but that's not necessary. Okay, one can define many different way. But okay, I mean, most of the time, whatever the binary operation one chooses, that time you had the identity. But here it is identity. Here it is about GCD. If you take GCD, you can choose any positive integer and take GCD of them. I mean, you will not be able to find a common element with whom, if you take GCD, you will get the main element. Suppose if you want to get a common element n naught, and if you want to get a common element n naught, such that if you take GCD of m and n naught, that has to be equals to n. That's what is the requirement, but that's not possible to get here. But interesting fact, a binary operation is said to be commutative, which is not required here, but still I am saying the binary operation star is said to be commutative if A star B is equals to B star A. If we consider the matrix multiplication, then the binary operation is not necessarily commutative. But if here the star is considered as the GCD of two positive integer, that's commutative binary operation. But that's not required and that's not asked here. But I hope it is clear why in this set with the binary operation does not admit any identity element. Okay. So this is what it is in the questions, and these two terms are little problematic. They are not completely correct. So whenever you don't have identity, there is no question of invertibility. Okay. So any other questions from all of you? If you have any doubt, whatever I am saying, even very trivial, it seems very trivial, you can ask me. I'll try to explain. This one, right? Identity. Okay. Yeah, okay, okay. So here the terms are like 1, 2, 3, 4, like this, right? So somewhere will be n plus 1. I'm taking n as general term, n plus 2. So, so identities element is some element which is fixed such that whatever element you choose from the set, if you do the binary operation with this by this way, you should get A again for all A belongs to the set, whatever the set here it is Z plus, this is what it is. So then we say that E is the identity. If this happens for all A, if there exists a common element E, common and fixed element D coming from the set, such that you should have this one for all A belongs to Z plus, then we say E is the identity. So whether let's ask one is identity or not. Okay, my claim is one is not identity. Because if you take GCD with 1 and 2, what is the GCD? Greatest common divisor, that's 1. But here, if we choose this is the A, E, and this is A, then you are supposed to get A here if you want to get the GCD, if you want to get the identity. But you are getting 1. Greatest common divisor of 1 and 2 is 1. So that's not what we are getting. We are not getting 2 here, we are getting 1. So that's why 1 is not identity element. I have said only 1 is not identity element. Similarly, if you take 2 here, let's take 3 then. Then what is the GCD? GCD is still 1, but we are supposed to get 3. We are supposed to get 3, but we are not getting that. We are getting 1. So 2 is not GCD. The 2 is not identity. So in this way, if you take any integer n and consider another integer m which is greater than m is coming from z plus and m has to be greater than n, then GCD of n and m, whatever it is, that must be less than equals to n, and that is strictly less than equals to m. But this is the n star m. If n is the identity, then n star m supposed to be m if you relate with this definition. But we are not. It can't be equals to m any situation, right? Because we have chosen m greater than m. Yes, there exist some elements for which it will satisfy this condition, but E will be identity if this condition satisfies for all the element A coming from Z plus. For all the element. So if you can give an element for which it is not happening, then we can't say that it is the identity. Clear? Okay. So I'm going ahead. If any of you have any doubt, still you can ask. I will stop the next questions. I'll try to explain this one. And any other questions from the course material, still you can ask. So let's read these questions. What this question says. Here what says, let m and n to positive n plus. What is n plus? N plus contains 0. Yeah, n plus means what is n plus? N plus means all n belongs to natural number such that n is greater than or equals to 1. So that's same with the z plus. So m and n be positive natural number. Then the subset zm plus zn, which is given by this way. Which is equals to am plus bn such that a and b coming from z. Okay, you know this is again an integer, so that will be subset of z. Z is the set of all integers. There it is. And m and n, but two positive natural number. This is what it is. Positive natural number. Okay. So what is the questions? First, we have to put the subgroup of the group z plus. Okay. So in the course material, there is already discussed what is group, but let me quickly go through what is group. Let let G be a set with a binary operation star. Okay, so if I am going little fast, you can stop me because uh, that's what sometimes it happens. I may go little fast, which is maybe not suitable to anyone. So you can pause me and ask me, then I'll try to be slow. That may happen throughout the complete course. Okay, so please don't hesitate to stop me and ask me to be slow. I will be slow. Okay. Let G be a set with a binary operation star, and mm, and then and G be a set with binary operation star and G binary operation star. So binary operation star means with G be a set which is closed with a binary operation set, which is closed with a binary operation. So what is mean by closed? That if you have two element A B coming from the set G, then A star B that has to be element in G. Okay, that's what it is meant by closed. Star is said to be group if first condition star is associative, that is A star B star C is equals to A star B star C. This is what it is associative. I have said already. Second, uh, G comma star should admit identity or unity, that is there exists an element E in G such that E star A is equals to A star E is equals to A for all A coming from the group G. Third, for every element, every A belongs to G, there exists an inverse of A in G. That is, there exists an B belongs to G such that A star B is equals to B star A is equals to the identity element. So that's the point. If you want to get the inverse of an element, you first need the existence of identity. Otherwise, you will not be able to give this description. So there, I mean, without identity, talking about inverse is, I mean, meaningless. That's what it is. So what it is said, I know this linear algebra, in linear algebra grouping things are little difficult because that's separate point, but that's something very basic. You just try to be little calm and try to understand. That's not much difficult. Okay, because they are the some little different type of backbone which is needed here. That means G is a set. We have given a binary operation. You can consider this binary operation as something like addition, multiplication, those type of things. But that's not necessary always. Okay. In Usually, if you take real numbers with addition or non-zero real numbers with multiplication, complex numbers with addition, non-zero complex numbers with multiplication, then all these properties usually hold. That there exists identity, associativity, and inverse. Those things always exist, but not in general. For example, if you take matrices, you will have identity, and consider the matrix multiplication, you will have identity. Associativity will also be there, but the inverse for every element that not necessarily exist. Okay, so this is called group. Group is a set with a binary operation given on it, such that it is associated with that binary operation. It will admit an identity element, and for every element A, there exists an inverse. So what's the example? Let's take real number with respect to the addition. This addition is just addition. A plus B means A plus B. That's all. This is a group. Similarly, if you take real number with non-zero real number with the multiplication, just multiplication, that will be a group. Here the identity element is 0. Here the identity element is 1. Okay. Here inverse of A is minus A. Here inverse of A is 1 by A. Okay. So these are the all group. So here what I have asked, we have given Z, M and N to positive integer Zm, which is equals to Am plus Bn, such that A and B coming from the integer. We have to prove that this is group. So first of all, this is closed. I mean, if you take two element like M and N fixed, so A1M plus B1M, this is one element. Another element A2M plus B2N, this is another element. Here A1, A2, B1, B2, all these are coming from the integer Z. Then if you add them, okay, sorry, here we have asked to find, this is with respect to addition. Okay, so I have said what is group, but I have not said what is subgroup. So let me give the subgroup, because I have to put subgroup. So what is subgroup? A subset H of the group G. We know that G plus G star is a group, that we know. Under that condition, then a subset, then H is said to be subgroup of G if for any A B belongs to H, A star B has to be in H, and A inverse that has to be in H. Or equivalently, this term is equivalently A B inverse belongs to H. So okay, here we have started G is a group. G is a group. So that means for every element you have inverse, right? So let's take a subset of G. So when we'll call that subset as a group, subgroup, I'll say that is a subgroup. If we take two elements from the H, if we do the binary operation, that the new element that has to be in H again. That's what it is called, the closed under the binary operation. Another operation is that we know if we take any element A in H, that is in G, right? But G is a group. That means we have A inverse. What is A inverse? That is some elements which satisfy this condition. That B here, that B is called inverse of A, and B is denoted by usually A inverse. Okay, so let me tell you one thing. We are still in the group theory and we will be going little bit field theory till. But whenever we will enter to the linear algebra, which you may enter in the next week, things are not will be that much. Things will not seems that much difficult. I believe so. When anyone start to reading the vector space, linear algebra, start things is there is a field thing. So that's why people used to start group. So, but those things are little different. They have separate literature. They have separate study. But linear algebra is little different. But you have to keep in mind arrangement of. Okay, let me see. What is it? Yeah, I will upload notes and as well as the recorded video lecture, the full recorded part. It will be available to you by 24 hours at the till from the end of the tutorial session. That hopefully will be available by 24 hours. Okay, so you can get the notes. This note, whatever I am reading, I am trying to explaining here. I will exactly share these notes in a Google Drive, and as well as I will upload the video in YouTube, and will share the link. And you may find those things in the NPTEL portal itself. Okay, and if you're not able to find it, you can mail me, or you can ask to any NPTEL person, or you can mail the NPTEL person. They will help you to find it. Okay. So what I have to prove, this is ZM is, I have to prove that this is subset of Z, and we are assuming Z with addition is a group. This is group, and what we know, the inverse, what is the identity? Identity is 0, and inverse, what is inverse? If we take A is an element in Z, then minus A is the inverse, because here the binary operation is just addition. So to prove this set is subgroup, what we have to do? We have to show that if we go to the definition, we have to say that A star B is in H. That means A plus B is in H. If we take two element, here it is two element, we can write it A1 plus A2 whole n plus B1 plus B2 whole n. So this element is again in this form, where A1 plus A2 this is in Z, and B1 plus B2 this is again in Z. So that's why this element is in this form. Okay, so this is closed under addition. This is the first condition we have asked for the whether addition is closed or not. Another is the inverse. So if we take any element Am plus Bn, that is in Zm plus Zn, which is subset of Z, then what is the inverse of this element? What is the inverse of Am plus Bn in Z? Just minus of that, what I have said, minus of Am plus Bn, which is actually equals to minus Am minus Bn, right? So, and question is whether this element is in the mother set. Here it is the subset, whether it is there. Yes, it is there. You can write this as like minus Am plus minus Bn. Here minus A minus B in Z. Okay, so someone asked for the lecture notes, then I have said the lecture notes will be shared and video will be shared. But still, I will encourage you to try to focus and try to understand in the tutorial session, because usually this what happens that you will feel that you will see the video later, you will try to read the lecture notes later, but that does not happen, because I am also a student. I am also I am also trouble. I'm also I mean travel this type of time that I think that okay, I'll take a look later, but that doesn't happen, and those things will that did not happen. You will see that exam will come again, and you will not have the time to read those things again. Okay? So try to focus in class. That to be better. And once again, if I am going little fast, please stop me. I will be try to little slow. So what we say, what is seen that Zm and Zn is a subgroup of Z plus. This is what it is. Is it clear how this is becoming subgroup? Yeah, I believe this is not clear to all of you, but if you have anyone feels that some point I have been a little fast or not able to, you can ask me. I'll try to explain. So once again, I'm saying what is the group? Group is a set. You have some operation. You can think that operation. You can consider a set, and you can think an operation that's the something like addition and multiplication for addition or multiplication for your understanding. What it has to be satisfied. You can just think like z integer set of all integer, and the operation is addition. So that is associative or not? That yes, it is associative. That means if you take three elements A, B, C, you can add A plus B, and after that you can add C, and that's the same with adding B and C and adding A. Okay, that means what I'm saying for Z, that A plus B plus C, this is of course same with A plus B plus C. Okay, so this is the associativity. So Z is closed under associativity, and identity element for Z, for this one, identity element is 0, because if you take any element and add 0, that will get A again, and 0 plus A. And inverse, if you take any element A and if you add this minus of A, you'll get 0. So that's why additive inverse is also there. So that's why Z plus is in group. It is the purpose of GCD mentioned in the question. Okay, GCD mentioned. What is the purpose of these questions, right? Okay, so purpose of these questions. This is the questions. What I believe the main reason to giving these questions is that binary operation is there. And what are the binary operation? I mean, that's common till 12, class 12. That's the addition, multiplication, and matrix multiplication. These are the binary operation common. But GCD is something that's hit very different way, but that's again a binary operation, which is associative, but that's very different type of binary operation. Similarly, LCM is also same type. Okay, but I believe that will be not much involved in the further literature. I believe so. Though I have not seen the upcoming things, but yes, that's true. That's true. So you are asking. That's the next question. That GCD is the generator of the set ZM plus. I mean, this actually, if you say these are actually questions of uh, field theory or group theory or modern algebra, that here we have seen that ZM plus ZM for two fixed positive integer m and n, distinct positive integer m and n. So this is again a subgroup, and this will be generated by GCD of m and z. That means these elements are multiple of GCD. Whatever element you choose, that will be multiple of GCD. Similarly, if you write ZM and union Zn, that will be, I think, union or addition. Sorry, intersection. Intersection, which I have not reached yet, that will be Z of LCM. So if you say that way purpose, but purpose in the this course, that's I believe not much. But these are the very interesting fact to know. These are very interesting fact in mathematics, that if you take two fixed different positive integer m and n, then Zm plus Zn is actually generated by. In fact, you don't need distant. You can take similar same also, but that's not anything, because if you take Zm plus Zn as a group, that is again Zm. Zm means all the multiples of integer multiples of m. Here it is all the integer multiples of m. So here it is. Yes. Right hand side part, LCM, least common multiple of m and n. Intersection, yeah, intersection. If you take two group and take intersection, you will get. I mean, if you take subgroup and take intersection, you will get a subgroup. So this will become a subgroup, and that subgroup will be. Though I am not going to discuss this part, I will discuss this part hopefully, but I am not going to discuss this part. LCM I will keep aside. I will only focus on GCD and all the related questions here. And the next question is this one. What is this one? So I mean, if you take addition of these two subgroup, that will be. I mean, ZM is itself is a subgroup of the group Z plus. Zn is itself is a subgroup of the group Z plus. I mean, set of all integer with addition. Their addition, if you take Zm plus Zn, that will become a subgroup. That will become a subgroup which we proved here, right? Of Z plus. That subgroup will be generated by GCD. I mean, that subgroup can be written like this. Similarly, you can do the same type of things with the LCM also. Okay. If I can get time, I hope I will not get time today, but if I get time, I will discuss this in the next session. If you wish or if you want to know, then I will discuss these LCM things. But I will today only focus, or may the other person which I mean maybe another tutorial will be there. There maybe this part will maybe discussed. Okay, so I will focus on this GCD this part. That's the next question. So if you have any doubt, that doubt maybe seems very trivial. I will encourage you to uh, I will encourage you to ask me. I will try to explain things. Yeah, here it is a question. Question is also not finished. Another question is that this is generated by this ZM plus ZM group, which I have proved that this is a subgroup. That is generated by GCD of MN. That means, so another task is that ZM plus ZN is generated by GCD of MN. So that what it is means, that is we need to prove that Zm plus Zn is actually equals to Z of GCD of Mn. GCD of Mn is a single term. Okay. So we have to prove that this term is actually scalar multiple of GCD of Mn. Scalar, I mean integer multiple of GCD of Mn. This is what it is you have to prove. Okay. So this is what it is the second term. This is what it is in the included in the this question, so which I have mentioned here, and which I have tried to do this here. So let's try to solve this. Interesting. Okay, so let's take S is a set that MNN fixed. Okay, sir, maybe you said it earlier, but I missed. But you can you please can you please recommend some reference book regarding group theory? Okay, group theory. Hartstein is there, but that will be little. Hartstein you can read. In fact, Damit Food you can read, but those are very standard book, and they are. I mean, you don't need much thing. You don't need group theory very much. I think after one and second week, you will not be use the group theory not much. Okay, so but I think Fredberg is there. Fredberg Incel, I think, as the name. Um, Hartstein, I think for basic things you can get Hartstein. There will be okay. Let me Hartstein. Okay, um, let me just buy Hartstein. There is a lots of book. Yeah, topics in algebra. The book name. The writer is actually I.N. Hartstein. Okay, but those books are not. I mean, you don't need much actually for the group theory. Another book will be easier book. If you say some, okay, I don't know anyone knows Sen Ghosh Mukhopadhyay. There is a book. That is also maybe named topics in algebra. That is also, I mean, for basic things. And the dummy food, that's, but those things are not much needed actually. You don't need, they are very standard book for the modern algebra, but you don't need modern algebra very strong way. If you need basic things, this is one of the book, but you may get the PDF of this book. You don't need to buy if you want to just read for casualty. This is the book, but that will be little difficult. That's the another point. This book may be not available in PDF form. If it is available, it's good. Um, okay. So, but I believe that's not. You can take any algebra book and take the first chapter, second chapter for the group theory. That's enough. You don't need to go very deep. Okay. Okay. So let's get back to the problem. Okay. Okay. Someone is referring some book. I don't know this one. And Isaac for okay. Maybe that. Maybe you can try. I don't have any idea of that book, but okay. So we have to prove this one. So let's take S is equals to um, S is equals to x m plus y n, such that collection of all this, such that x and y is coming from z, but the condition we are setting is that xm plus yn is greater than 0. First of all, this is a set. I have said this is a set. The first thing what we saw that, okay, whether this set is empty or not, whether does there exist any positive thing. The S is non-empty, which is denoted by S is not equals to empty. This is the empty sign. As why this is, you can take x equals to minus m, and sorry, you can take x equals to m and y equals to n. Then what will have that xm plus yn, this must be equals to m square plus n square, and that is always greater than 0, because we have taken m and n positive integer. So they, as the positive integer, this is positive 0. So S is non-empty. Now, as S is non-empty, so any, and it is set of all integers. This is also set of all integers. So then S will attain a in smaller element. S will attain a smallest element. That means there exists an element. We can say that A, okay, in S, such that whatever element be in S, that will be greater than or equals to B. And why that exists, that's maybe you can think using the pigeonhole principle, but I'm not going to discuss. But you can clearly convince that if you take a set of all positive integers, if you take a subset which contains positive integers, some positive integers, there will be smaller positive integer among them. That's very convincing, but that's standard way. If you say using pigeonhole principle, you can prove, but that's the very axiomatic way. But you can think that there exists a smallest integer. That's what it is needed. So let's take that smallest integer. Let b is that smallest positive integer, that smallest positive integer in S. So what my claim is that this b is the GCD of m and n. So this is what it is my claim. So we'll prove this one. So if you can prove this, how I mean, first we'll prove this, and that will help that prove that the group which we have first started, that will be divisible, that will be generated by this GCD. Okay, so by the division algorithm, which is also one of the problem here, but I hope I will not discuss that. And by the division algorithm, what we can say clearly note that if you take x is equals to 1, y is equals to 0 in these settings, that xy plus yn, then what will get n. Okay, similarly if you take, you will get then xy xm plus yn is equals to n. If you take x is equals to 0, y is equals to 1, then we will get n, right? And they all are in the set S, because m and n both positive, right? But b is the smallest one. M and N both are in S, but D is the smallest element in the set S. So that means D will be less than equals to M and N both. Then by division algorithm, M, there exists unique Q and R integer, positive integer. There exists unique positive integer Q and R such that M can be written as QD plus R, but R has to satisfy the condition. This is what it is. This is the division algorithm. The next questions maybe this was the next questions, but this is the, I hope many of you know this division algorithm, but if you don't know, just read the statement and that is very standard. If I get time, I may try to solve this. But division algorithm says that just take two positive integer, one is bigger, one is smaller. Okay. Then if if M is the bigger one, just think like this is right now. Think that D is less than equals to M. Then there exists two positive integer Q and an R, such that you can write M equals to QD plus R. Something like that. Take D like that. Take M here and start to divide by D. Okay. So whatever the largest in multiple of D will be there, you can like okay. Let me tell you very with an example. Let's take 7 is the M and 3 is the D. So what I can write, 7 can be written as 2 times 3 plus 1. This is the R, this is the Q. You just divide, try to divide it, and whatever the, what is called, that's dividend. This is the residual, I know, but what this term is called. Okay, I forget actually. So this quotient, this is the quotient. Q for quotient, R for residual. Okay, that's why QR is a standard notation. The quotient and residual. This is what it is. Okay. But and this R will be less than equals to D, and this is the standard. I mean, this is the theorem. Then by division algorithm, there is this unique positive integer Q and R, such that this happens. Okay. So that means R is equals to M minus QD. So note that our target is to prove D equals to GCD of Mn. Okay. That means M is equals to Q of what is, we know D is equals to, D is the smallest positive integer. That means from here we can say one thing, D is in S. But what are the elements in this? They are X, M plus Yn. That means there exist A and B in integer such that D is equals to AM plus BM. Because D is an element in S and the element in S are look like this way for some positive integer A and B, for some integer A and B, not positive. So here we can write M minus Q into, I'll write D is equals to this one, that AM, A is an integer, just to know that this fact. AM plus BN, which can be written as 1 minus AQ whole into M plus minus QB N. So again, this is XM plus YN form, right? Again, this is in XM and YM form, right? So that means this element is in S, because S consists, annual elements look like this way, that Xm plus Yn, where X and okay. Also we know that R is positive, R is greater than equals to 0. Okay, so if no, we can't say X plus Y. This is from for, okay, for some X and Y belongs to Z. Now, if R is not equals to 0, that is 0 less than R less than D, then R is equals to 1 minus AQ plus M minus QB whole N. This must be an element in S, because this is R is positive I have taken, and S elements are of the from this XM plus YM, but this has to be positive. This is the S set, right? So this is what it is. This element is this one, but R is less than D. But we have considered D is the smaller element in S. So that is a contradiction to the assumption that D is the smallest element in S. Okay, that is a contradiction, that D is the smallest element in S. So that is what will get, R has to be 0, because if R is not 0, that will contradict the fact that D is the smaller element in S. So R has to be 0. If R is 0, then what we can write, M is equals to QD for some Q in the positive, for some positive integer Q. Similarly, here we have started with the fact that D is less than or equals to M, and we obtained that D divides M. So this means, okay, that is D divides M. This is what is divide sign. So if we start this, all this, whatever we have done from here, using the division algorithm and whatever it is, if we do all these things in the place of N, if we replace N, then we get, similarly, D divides M. That means D divides both M and N. Then by definition, definition of GCD, D divides GCD of Mn, right? Then D has to be less than or equals to, okay, but also recall that D is equals to Am plus Bn for some fixed A and B in the integer, right? But also the fact that this is positive, that's another point. If so, if we want to prove that D is the GCD, what we have to prove? If there is any other common divisor, if there is any C which both divides both M and N, then C has to divide D again. Then we can say D is the greatest one. Whatever the divisor is there, D is the greatest one. Then D is the GCD. Okay, so let C is any other divisor. Let C is any other positive divisor of M and N. Then C will divide AM plus BN, but this is what it is D, because C divides M, C divides N, C will divide AM, C will divide BN, then C will divide their addition. Okay, so that means C divides D. Then by definition, GCD, D is the GCD of Mn. So this is the claim we have started, that D is the GCD, but not yet, we have not completed the proof. Our proof is that, recall that our target is to show, our target is to show the set Zm plus Zn is equals to GCD of Mn Z. That means whatever the element I will choose from this Zm plus Zn, that has to be look like that way. That has to be some scalar multiple of, integer multiple of GCD of Mn. Let some other notation I need. S and T are two positive integer Z, and Sm, they are arbitrary. And Sm and Tn is in Zm plus Zn, right? Now by definition, GCD of Mn that divides M and N, that says GCD of Mn that will divide Sm plus Tn, because this term separately divides M, separately divides N, so sum, this will divide the sum. So that means you can write Sm plus Tn is equals to GCD of Mn into some, what are the other notation I can use? Q, I can't, A, B, C, D, F, G, H, I, J, K, L, K. For some K belongs to integer. Positive, negative doesn't matter. I can say that there is just K. So this K is coming from this. That means Zm plus Zn, if I take any element from here, this element is in Z of GCD of Mn. Okay, so I can understand. So many people who are not able to understand that I can recall. Let me complete this one and after that I'll say. This is subset of GCD of Mn, but we have to prove the other around. That this is also subset of, but that is already standard. Why this is subset? Any element, recall that B is equals to GCD of Mn, and that is equals to Am plus Bm for some fixed A and B coming from the integer. They did not need to be positive. Then any element that will be something like k of Am plus Bn. Yes. That's contained in this. Yeah, that's an element. I have taken S and T sub, not subset. Sorry. Thank you. This, so one element is there, right? So we have started an arbitrary element S and T in Z and this. And what are the element in Zm plus? What are the element in Zm plus Zn look like? You can choose one integer from here, one integer from here. That means that will be element for some S and T coming from Z and Sm plus Tn. This type of elements, right? So as I have chosen S and T are two arbitrary integer, any element in this form, so we can say, yeah, thank you. This is the mistake I made. Zm plus Zn, that is actually subset. Oh, sorry. This is Zm plus Zn. This is the subset of ZCD. Is it what you mean? No, this is the correct thing, but this is what it is. I am supposed to write, but I written wrongly. I mean, this is the actually, I understand. Most of you are, I mean, how many of whatever, I mean, how many of people who are already attending this course right now are the first year or the first semester of the mathematics, whatever you're doing, or very first time you are learning mathematics? I think most of you are doing the mathematics for the first time. This will feel little different, yeah, but these are the way mathematics works. But these are something like logical and whatever you know till now, that okay, doing some integration, those are also mathematics. Third semester, okay, Presidency University, good. So then these things are not very new to you. You can understand things very clearly. So, but third semester means the second year, okay. So these things are very, I mean, these things are known to you, but whoever is the first year, they need little time, but at the end you will enjoy these things. I believe you will enjoy these things, but first time it will feel little bore, because this all the logical type of things. And okay, so okay, so but I believe whoever is just in the completed the first year, for them it will not be much difficult. I mean, maybe difficult but not much. But whoever is first year or the first semester, they will be little difficult. But if you try to understand, at the end you will be able to understand. But whenever we will enter the core linear algebra things will be little very different. These things will be different from here. Okay. Okay. So okay, what I'm trying to say that we have proved this side. Whoever corrected me, thank you for that. We have proved this side. We have proved this side. But if you want to set this is equal by usual set theory says that I have to prove the other side. So other side element are this one, that if you take any element in JCD that must look like this way, then you can write it as Ka whole m plus Kb whole m. Here a and b are two fixed integer, but k is an arbitrary. But Ka, Kb they are integer. So that means this element is in Zn. This is in, not subset. This is in Zn. Okay, this is not subset. This is something. This is an arbitrary element in Z of GCDM. ঠিক আছে, let k is an arbitrary element in Z, then k of GCD of Mn is equals to k. We know, we have fixed what is GCD, that Am plus Bn. That's what it is, that for some fixed AB in Z, so that will look like Ka whole m plus Kb whole m. That will be subset of Zm that will contained in Zm. So that means I have started an arbitrary element in K Z GCD Mn. So we can say that Z of GCD of Mn that is contained in Zm plus Zn. So that will say Z of GCD Mn is equals to Zm plus Zn. This is what it is we targeted to prove. So that means the subgroup Zm plus Zn that is generated by GCD of Mn for two distinct positive integer Mn. Okay, so lots of things I have tried to explain, but I don't know how many of you are able to track things. But I will encourage you, even if you are even at least even one question is I am able to solve one question in throughout the live tutorial session, and that's complete clearly to all of you. That would be better instead of doing more questions. So if you have any doubt, any difficulty understanding anything, or not able to clearly listen to me, or not able to clearly listen to see the screen, you can pause me, you can ask me. I'll try to explain things once again. Yeah. Yes. Okay. What we have done, that what we have to prove, that Mn and two positive integer is there. We have to first prove that Zm plus Zn is equals to Z of GCD of M. So GCD of Mn. So GCD of Mn is a single number. You can consider this is D, something like that. And D is also positive. If Mn is positive, D is also positive. So in this question's first task was that this is a subgroup, which we proved separately. Second task is to prove this one. So what we have first proved, that we have taken a subset S, which is actually look like this way, xm plus ym. So that these are element in here with x and y is coming from z. So that means this is subset of zm plus zn, right? But we have added one more important condition, that xm plus yn is greater than 0. And we have proved that S is non-empty, right? And their existence, as this is a set of all positive in set of some positive integers, so there will exist a least positive integer. If you consider any set of positive any subset of positive integer, there will always will find a least number which is in that set, right? Let's take D is that number, and as D is that number, D must be equals to am plus bn for some fixed a and b coming from the integer, right? We have proved that D is actually that GCD of this Mn. We have proved this. This is another step. So after this, proving this, we have proved that Zm plus Zm, that is equals to Z of GCD of Mn. So if you just don't able to relate how this S is helping here, you just think that we have this S helps me to find GCD in terms of this, which is using for to prove one side of this equality, and in fact both side of this equality. I believe both side. One side is clear, that's in the uh, no, one side. It is helping to prove this side of the proof. Another side is automatically by the definition. This is what it is, the step-by-step thing we are doing. I mean, this S description seems like came out of nowhere and doing some very lengthy things. So this S things is helping to find that D is in this specific form. You will find an A and B integers for which D is actually can be written as M plus Bm. Okay. There is another way, but that different way, that if you take two positive integer, then GCD can be written like this way. There is another way, that's division, through the division, but I'm not going that way. Okay, is that okay? These are the steps I'm doing. In between, I mean, this is the main major step I'm doing in this problem. Okay, so is there any other doubt? Is it clear? Whoever asked, I did not. Okay, so any other doubt? Okay, so thank you. So let me see what are the other problem is there, but I will go to vector space. I'll try to be go to vector space. That will be better. Okay. So there is many more things using commutativity. Okay. So my main target is to solve something which will help to solve your assignments. So there is another problem which I should solve, which may help to solve the other problem in the assignment. Okay. Okay. So okay, let me solve the other problem. And I was thinking to go to the um, I was thinking to go to the vector space, but I think that time I'll not get that time. So let's do this, and after that, if I get the time, I'll try to solve this. This is not difficult. This problem I believe not difficult. So what this problem says, um, let a and b two real number. Okay, if a and b is a map from R to R, which is given by f a comma b at the point x is given by ax plus b, and for all x belongs to R, this is how it is defining this map. Then the set, this is called affine linear maps are, but don't go that, don't, um, if you are not able to understand why this name, but forget about, but just consider these are the collection of functions with the condition this one. Okay. Then, with the composition as binary operation. So what is the binary operation? This is a binary operation. Define a binary operation. Star on this set. This is considered just a set. Okay. By let's take A1, B1. Okay. And I mean, you can get F AB. Another is F CD. Right. So here A and B both real number and A not equals to 0. Similarly, C and D both real number and C not equals to 0. So here is a composition binary operation. So if A comma B star if C comma D at the point X is the composition, that if A comma B at the if C comma D X. This is what it is. How will be defining if A comma B? This will be Cx plus D. This is the definition, and this is going to be A Cx plus D plus B. This is first, it is that A Cx plus AD plus B. This is the composition. So here it is said that with the composition as as a binary operation is not a commutative group. So to prove group, once again we have to do the associativity property. So let's check associativity property. A B C D E F. Let's take another F A B star C D and with star F E F. Oh, no, I cannot use E and G. E and G and at the point X. So what will have F A comma B star F C comma D. This is a composition. Composition of F E comma G at the point X. That is going to be F A comma B star F C comma D, and this is Ex plus G. And if you look at the composition of F A B C D, that will be AC X plus AD plus B. So here X is this full term is the X. So this will be AC Ex plus G plus AD plus B. This will be ACEX plus ACG plus AD plus B. This is first composition of this and with this. This is what it is. Another one is FAB star one second. Just okay. Sorry to interrupt. So this will be F A comma B at the point F C comma D star F E comma G at the point X. This is what it is, right? So but what it is, you can look at, you can try to replace this A C A D plus B that way. If you do this all this, then you will get C E X plus A C X plus A D C G. I hope I'm going correctly. D. This is what it is. Now A of C E X plus E G plus D plus B, that will be like A C E X plus A E G plus A D B. This is A E G. Oh no, A C G. Just a minute. Did I make some mistake? C D E. This will be C E X C G. This is correct. A C E A E G. But here it is what is coming. Just a minute. This is A C G. This is correct. This is correct A C G. So here it will be C E X C E X C G. That's 2 plus D. That's D. Okay, so you can look at, okay, there is another way. So another way to look at this thing. So that will be little easier, I believe. So this is little lengthy. I am trying to be little short. So we can write this one as f of AC, comma AD plus B at the point X. I can write this one because that is the definition of this one. So if we write f AB star f CD whole star f EG, then this will be like f of AC, comma AD plus B star f E, comma G. So by this definition, what is this will be like first term, second term, and first. This is the what is definition. So if you go that way, you'll get A C E, comma A D. That is, here it is. This is A and this is D. So A C G plus the, oh, this is B, A D plus B. This is what it is. And if you go that other around, A comma B star F C comma D star F E comma G, this is equals to F A comma B star, it will be F C E, comma C G plus D. This will be F A C E, comma A C G plus A D plus B. Yeah, this is correct. If you use this formula, you'll get this. So the associativity. So star is associative. And what is the identity? Identity, let us consider, take A is equals to 1 and B is equals to 0. Then f ABX is equals to AX plus B, that is equals to AX, that is equals to AX. So for any AB composite star with F, this one we'll call, this is the um, 0 1 0 1 0 at the point X. By the formula, what will get? F of A, comma A0, that's 0 plus B, B. This is what it is. And that is, once again, you can prove that F10 star F A comma BX, because that is what it is. 1 with A, that is A, 1 with B, that is B plus 0. You can use this formula. You just use this formula once again. So that is F1 comma 0 is the identity element of the binary operation of this affine group. What is the notation? Yeah, affine 1R with star, and inverse is there or not, that's separate point. Whether inverse is not, inverse is there. So what will be the inverse? So you can check here. I'm not going to discuss little general. I'm just going to directly, let's take A and B in R with A not equals to 0. Then I'm going to discuss what is the inverse of FAB. That is, what is the inverse of FAB? Inverse of FAB will be FAB inverse. That will be F of A inverse, comma A inverse B. We can calculate. Okay, let us calculate them. This is, so why it is happening. Let's take that there exists C and D. There exists C and D are such that if A comma B star F C comma D, that is equals to identity. That is equals to identity means F1 comma 0, that is equals to F C comma D star F A comma B. So if this happens, what we know by formula, F of AC comma AD plus B, that is equals to f1 comma 0, that has to be equals to f of ca comma cb plus d. That's what it is. So that means what we got, ac is equals to 1 is equals to ca if we equate all of them, and ad plus b, that is equals to 0, that is equals to cb plus d. So we have to find c and a. Then we can say this c and d, this term, this is inverse of fab if the below equation has a solution in real number. So if we can find c, we got what is c? C is equals to a inverse, right? If we can find what is d, then we are done. So if we try to find d from here, what will be? D equals to minus b into a inverse. I think minus it will be there. I think minus will be there. Yeah, I hope I have written minus here. So it will be here will be minus. This is what I'm misting, minus a inverse b. So this is d. So that means what we got, if a comma b with star, if c is a inverse comma d is minus b a inverse, this is turns out to be f1 comma 0 is equals to f a inverse comma minus b a inverse star f a comma b. So inverse for each element in this affine 1R exist. I don't know whether this is clear or not, but is it clear how the inverse is working? How actually this is also says if you are giving a group how to find the inverse of some element, which are very non-trivial. You know, if you are giving the set of all integers, how to find the inverse, and with addition, if you take 2, what is the inverse? Minus 2. If you have the multiplication, if you take a non-zero real number a, what is the inverse? 1 by a. But this type of situation, inverse is not that much direct. You have to calculate whether inverse exists or not. If you try to understand carefully here I have started that there exists C and D for which this hold. Inverse will exist only then whenever this type of situation have a solution. Okay, and here we can see we have the solution. If you use this one, still you will get the same solution. What is D? D is equals to minus CB. And what is C? That is A inverse B. They are both are same because AB real, AB commutative. Here you can write because AB real number. That's all. So inverse for every element exists. That's what it is. My point. Is it clear? Yeah, maybe going very hard. I don't know. So here actually we have a collection of functions. What we are doing? Let me summarize this. What we are doing? We have a collection of functions which is defined in some sense and a operation. That's the composition. What we first proved, associativity of that operation. But before that, what we established a formula. If we take two composition of these two, what we'll have? We have this type of things. We will have a new function which is corresponding to this number. Using that, we have observed the associativity of these two equality. Another is that the identity. If we consider A is equals to 1, B equals to 0, then we have this one. This is identity because if you check with any AB, you will get that function once again. So that's why it is identity. Whenever there is identity, one will ask to check whether there exists inverse for every element or not. So here if we start an element A and B with a not equals to 0, why A not equals to 0? Because we needed A inverse. If A is 0, you can always define the function. There is no problem. But you will not be able to get the inverse. This is the point. If you don't get the inverse, then you will not be able to find the inverse of the element FAB in that set with the binary operation composition. So to get that inverse of the function fab, you have to consider a is non-zero. That means a is invertible in real number with just multiplication. And with that, you can check, you can consider, you can start with calculation from here. You will able to find C and D, which is working as the inverse. Okay. So if there is any doubt, you can ask me anytime. I'll try to explain. But so what we proved actually, all of this we have proved three property: associativity, existence of identity, and another is the existence of inverse for every element. That says this set is a group with respect to the binary operation composition. This is what it is. But the main question is that composite is not always associated. Uh, composite is not always associated. Composition is not always associated. Let me think an example. Composition is associated if we say f g h3 function, f compose g compose h x is equals to f compose g at the point hx. That says f of g of hx. This is what it is. This is what it is. And that says, yeah, that's true. Composition is always associated. Composition is always associated. So you don't need to do all these things then. You can directly say the composition of two function, three function, the composition of function is the operation composition of function is associated. That's true. Yeah, that's true. Composition of functions is always associated. Okay, so the final thing what I need to prove here is that this operation, this composition is not commutative. That's what it is. So we have to create a counter example. That means we have to find for the claim this composition is not commutative. What is commutativity? That if we take two elements G1 and G2 from a set G with a binary operation, commutativity means G1 star G2 that has to be equals to G2 star G1 for all G1 G2. If you have this fact, then you can say commutative or abelian. But here we have the composition as the star, so we have to prove either it is associative or commutative or not. If AB belongs to R with A not equals to 0, and similarly take another pair CD belongs to R with C not equals to 0, then we have one function AB, we have another function CD. If A comma B compose F C comma D, that star is equals to F C comma D star F A comma B, if this happens, then we say compose. Let's see if this happens, what are the conditions we are getting. If this happens, then what will have? This will be f of AC, comma AD plus B. This is the definition I have said. Then this will force AC, comma CB plus D. That is, we need A, B, C, D with A not equals to 0, not equals to C is not equals to 0, such that AD plus B is equals to CB plus D. So if you can find, we need this fact. If you can find, because AC is equals to AC, there is no problem with the second coordinate. So if you can find ABCD where A is not equals to 0 and C is not equals to 0, but this equality does not hold, then that will be counter example. But this not always holds. For example, okay, let me create A can't be taken. If we take A and C both 1, then it will be. So we can't take A and C both 1. So let's take A is equals to 1, C is equals to 2. Then what will happen? If A is equals to 1, C is equals to 2, then it will be like D plus B is equals to 2B plus D, right? So in that case, why that can't be equal? You So if you take B is equals to 0, that will work, and B is not 0. So let's take B is equals to 1. So let me show you why. Take A is equals to 1, C is equals to 2, and B is equals to 1, D is equals to 0. Then AD plus B. What is A? D, that's 0, plus B 1. Okay, and CB plus D, that is 2 1 plus 0, that is 2. So of course AD plus B not is equals to CB plus D in this case. So that means if it is commutative, then we necessarily should have this fact. This fact has to satisfy for all the choice of A, B, C, D for which A not equals to 0 and C not equals to 0, for all the choice of A, B, C, D with this condition of real numbers. But here we got choice A, B, C, D where A and C not equals to 0, but other can be 0. So where this inequality does not hold. So commutativity does not hold in general um, affine 1 R with the binary operation addition. So at least is this commutativity clear? One thing I'm using repeatedly, that is f a comma b compose f c comma d, that is equals to f a c comma a d plus b. This is what it is I'm using very repeatedly, and that's true, that I have established first. Okay, so any doubt in this particular problem, in this particular problem that we have started to prove that this affine set is commutative group, but that affine set is a group but not a not commutative. This is what it is we prove. Is it clear to everyone? You can let me know if there is any doubt. There is any doubt or any point where you are not able to understand why these things are happening. I hope my speed is little fast. I will try to be little slow. But whoever is afraid with all this group theory, I just want to assure you that after 1 or 2 weeks, this much group theory or algebra will not be there. Only linear algebra will be there. Vector spaces, linear operators, basis, and yes, well, basis, linearly dependent, independence, all these things will be there. Okay, so if you have any doubt, please feel free to ask. And I will not solve any more problem today. I will, if there is no doubt, I will close in few minutes. I'll wait for a few minutes. If you have any doubt, just let me know. Oh, sorry. Yes, this is one fact. Someone told me that this associativity composition of functions are always associative, for at least for real valued or complex valued. That's very good point. I have not pointed out. So we don't need to calculate separately. So that will be there, but still we need this fact, that f of this fact is needed, that f a b star f a c d, that will be f a c plus a d plus b. That's um, yeah, answer may be brief, that's true, but I don't know why this type of problem is there. I mean, problem is, um, but I believe few days, after few days, um, I mean, after 1 week,